The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, today I'm going to talk a little bit about computer architecture and how computer architecture impacts performance engineering. So the main part of it is going through a long overview of the Pentium, the Nehalem architecture that is in the machines that you guys are using. This is the hot off the press 6-core processor that's out there now. And then I will talk a little bit about profiling a program. And then the next lecture, the TAs are going to demonstrate how to use some of those profiling tools that you guys are supposed to use for the project 2. And I guess the project 2 will probably appear, since we had a delay, it will probably appear 24 hours delayed. We'll release a project 2 up there. And then at the end of the talk, I'm going to, in the lecture, I'm going to talk about a little bit of examples. Go through some programs and show what you can gain by looking at things like profiling and what information that you gain. Just kind of give a high-level view. So let's start something interesting. So how many of you have seen, how many of you had held a chip in your hand, microprocessor in your hand? Some. There are some people who haven't. So I brought some show and tell things. So what I'm going to do is pass them around, and there are two things that are actually very valuable that I want to collect at the end, make sure that they don't get damaged. So this is a Pentium 3 that's already in a big heat sink in there. Okay, so you can't see that much, but they did a cute thing. They created a hologram of the chip and put it there, so you can catch I guess people who are trying to use counterfeits and stuff like that. So this is AMD K6 with the packaging in there. I'm going to send it around in there. Okay, and this is Pentium Pro. Normally what happens is that when the first die comes out, this is humongous, gigantic die. But as a couple of generations, what you do is you take the same circuit and you shrink it and shrink it. This is probably about 2 shrinks ahead. So the actual die right now is very small because this is a couple of 2 generations later process that things have been shrunk. This is a Core 2 Duo. Okay, so this is, I think there's 2 cores in there. So I didn't want to bring anything newer because those chips are darn expensive, and if you touch it in, basically you just static will basically destroy the processor. So these are something that came out of things that doesn't work. So the next 2 things, these are, I really need to get this back because these are like the only thing that's the one available in this world. Basically, there's only one of items. So at MIT, we built a processor a couple of years ago called a raw processor. So here's a raw die before it's being mounted. So this is what comes out after all the fabrication before it goes into this mounting with all the pins. If you look at the top of this one, what you will see is all these dots, which are basically where all the pins go. So you don't actually even see inside the die in this one. However, then you pay a bunch of money to these people who go and grind that chip. You take a real working chip and you grind it and expose insides of the chip. So this is a ground chip that's exposed the metal layer. So in fact, this you can see real circuits in the chip. So I don't think anybody has the vision that's required to see the transistors or even the circuits. But it's kind of interesting to see. So here are these 2 things. So some show and tell items. Okay. Aha, and this is the entire reason that microprocessors are not getting faster anymore, because this is one humongo heat sink that you put in the modern machines, and there's a huge fan that goes above that, and you can't keep building larger and larger heat sinks to get the heat out. And so that is why the heat is paramount, and that's why we can't run 4 gigahertz, 10 gigahertz processors. We are stick into the current kind of 3 gigahertz range, and then we are getting multiple cores. So it's a big humongo block in there, and then some machines even have bigger blocks. Okay, so while those things go around, let's start the lecture. So computer architecture includes many different things. You are doing instructions, memory, I/O bus, disk systems, GPU, graphics, all those things. But we are not getting into beyond instruction and memory systems. So we are going to focus on that. But if you really want to understand the full end-to-end performance, you have to worry about all those other things. So that said, let's go into instructions and memory. So here is the Nehalem processor, and there's a beautiful picture of the processor in the left. This is the kind of the raw chip that I'm showing you. They have ground out the upper layers, and you show some inner layers in there. And so that's what you get when you buy the Nehalem. And this very complicated diagram in the right side it's the abstract notion of what's happening inside. So what we'll do is go a little bit into this right-hand diagram and trying to understand what impact it will have on you. This is not architecture class, but you as trying to get performance has to make sure all these components work pretty well. That said, it's very hard to understand in a modern microprocessor exactly what's going on. Not even Intel understand what's going on most of the time. And so a lot of things, it works both ways. So you can't ask exactly, tell me exactly what happened or get there. So you can be fuzzy. On the other hand, being fuzzy means there's a level of abstraction that you have to live with. And what that means is when something gets hit to your head very hard and have a really bad situation, you can see that and you can react to that. But there are a lot of small things that happen. These things interact in very complex ways, so you don't understand exactly into minute detail what's going on in these machines for a given application, because a lot of different things might work different ways. So that's it. So if you look at what you learned for 004, so what you have is instructions. So you have here 2 instructions, one after another. So each instructions take about 5 cycles. So if this is a non-pipeline machine, so you look at why it's probably taking 5 cycles. So that's because it's doing different things. You are doing instruction fetch, instruction decode, after that execute, then you do some memory fetch, and then finally write back it in there. So you do all those things running one instruction, and then you start the next instruction. Of course, this is very inefficient. So the first thing people realize is, wait a minute, after I do instruction fetch, that logic that do instruction fetch is not doing anything for a while. Why don't I start the next instruction fetch immediately? Because you are doing the same circuit, and then every cycle that circuit can go do the next thing and next thing and next thing. And by doing that, voila, I can basically every cycle I can get an instruction through the system. So this looks very nice and simple, and you can get. So what are the issues in here? Is the world this nice and simple? No. Okay, what might happen?
You have like unbreakable branches or things that you can predict.
You have a lot of issues that normally cause hazards. So there could be 3 different types of hazard. There are things called structural hazard. What you're trying to do is attempt to use the same hardware, do 2 things, but there's only one hardware, so you can't get 2 things done. One has to wait after another. And there are things called data hazards. That means you're trying to run these things one over another, but logically, they have to run sequence serially. So that means there's a data dependence I'll get into that makes it impossible to make these things run in a pipeline fashion. And finally, there's control hazard, things like branches and things like that come and interfere with that. So let me get a little bit detailed down here. So the first thing we have is what we call data hazard. I will talk about true dependencies. So before I go that, I will share a little bit of this assembly representation. In 2 lectures, you are going to get a more deep drilling into how to go from C to assembly. But before that, so what this instruction says, this is the normal x86 form. You are doing add long, add in to the values in this RBX and RAX, and put the results back into RAX. So you are doing RBX plus RAX and get the results into RAX. Here subtracting RAX with RCX and put the results into RCX. So basically always the results is in the right hand side. 2 operands are basically the first and second. So the last one get as read and modified. Okay, so that's the way to read it. So I will have few question.
Instruction 1
instruction, if dependent on count. So the second instruction is data dependent of first instruction. So what's happening is I am writing this value here, which will be read by this guy here. So I write something, and the next instruction is reading that. The problem is if the right thing must not be available until very late in the pipeline. So we cannot execute simultaneously and overlapping basically of this dependence. This is called basically read after write hazard, because I'm going to read after it's being written. And if you look at the pipeline here, what happens is the write happens here, and the next read has to happen somewhere here. So until this one, this write, this read can't. So these stages has to get delayed up to this point. Does it make sense? Okay, because I'm trying to in here read something that's not going to be produced for 2 more clock cycles. So that's not available, and I can't do that. Make sense? Okay. So the next type of dependence is called name dependence. There's the dependence called anti-dependence. Basically, what it's doing is it's 2 instructions are using the same register, and because of that, I can't start using the register until the other one finishes up with the register. So in here, what's happening here is I am subtracting RAX and RBX and putting the value in RBX. And here I am adding RCX to RAX and basically putting the value in RAX. The problem here is I cannot modify RAX before this guy has read the value in here. Okay? So that means I am trying to go modify it and say, no, can't touch it because somebody else still want to get the value and I can't go destroy the value. And I have to wait there. That's the first type of what we call anti-dependence. And because both are using RAX, there's no real data movement, but it's basically have the same space. I have to wait till the other person can be evicted before I can rewrite that register. So these are called write after read hazard. The other type of dependence is called output dependence. So I'm updating RAX twice, and of course, in this simple example, we can probably even drop this instruction because it doesn't matter because I'm rewriting it. But if there's something in between also reading, so what happens is I can't do this in the wrong order. So the last value that updated has to be this instruction. So we have to make sure this instruction happens after this instruction. So we have a dependence in this. So there's some ordering in here that has to be maintained. Okay, and it's called write after write hazard. So instructions that have name dependence, we can actually get rid of the dependence by what we call register renaming. So everybody uses RAX, so that's kind of artifact of good old Intel architecture. Sometimes they didn't have that many registers, so you have to use the same register for many things. So in a modern, inside the hardware, there's what we call register renaming. So you have a lot more slots for the same registers, and so we say, even you are using RAX, this is the old one, this is the new one, use a different location for the new one. So I can do renaming, and then basically in hardware I can get rid of that. The next interesting thing is control hazard. So here what we say is, if you have this kind of loop, S1 is control dependence on P1. So we can't do S1 until P1 is done, or S2 until P2 is done. So we have to wait till the P1 condition is resolved before I can do S1 and vice versa for the next one. So the interesting thing is control dependence. Also, we can get rid of it by doing speculation. So the idea there what hardware does is it will say, wait a minute, I know I have to wait till P1 is resolved to do S1, but I'm going to do S1 anyways. I will just go do S1 speculatively, and then at the end of doing that, at some time when P1 is calculated and I know what the P1, I said, okay, did I do it right? If I did it right, I am good. If I did something wrong, I have done some extra work that is not useful, throw it out. Question?
If the speculative branch changes some portion of memory?
So what happens is there's a thing called a write buffer. There's the complex thing is at the end of the day, the instructions has to be get committed in the order they arrived. Okay? So before committing, you keep the state in buffers without really sending it to the memory. So write back into memory doesn't happen until the commit point. Okay? But when you read something, before reading the memory, it say, okay, have I updated something? Is it in the right buffer? So I read things from the right buffer in there. So you have to do in-order commitment, because you can't do out-of-order commitment. That can do crazy things. You do in-order commitment, but inside the machine, things can go all this in there. I'm just kind of jumping the gun a little bit. So in a modern Nehalem processor, these are kind of Intel proprietary, so you don't know exactly what it is. In some place it says it has 16 clock cycles, so it says it might be 16 stages of pipeline. And another place it says 20 to 24 stages of pipeline. So, okay, if you work for Intel and sign the NDA, you will get the exact number, but it doesn't matter. It's a lot of pipeline stages, so that's all you need to know. So what happens is you are doing this instead of 5 stage, that like what you did in Power Beta, you do instruction decode, instruction queue, pre-decode, queue, decode. This is register rename and allocate registers. And then there's thing called reservation stations that wait for when data is available to execute that instruction, and then execute, and then basically go that. This is what normally instruction life would be, if everything goes one after another after another. So what to get out of this is the pipelines are long. Okay? And so pipeline stalls and stuff can be expensive. So the other thing you can do in abstract way is do multiple issue. So if you do pipeline, what happens is you do one at a time, and so you can use the pipeline stages nicely. How about instead of having one unit, if you have an integer unit and a floating point unit, and every clock cycle you can basically in abstract you can say, oh, look, I'm taking integer instruction, I'm taking floating point instruction, and taking both together to the end, and then voila, at the end of the day, in one clock cycle I can retire 2 instructions, one integer and one floating point, if you have 2 different sets in there. So this is also very nice. You can get a lot of what we call superscalar performance. However, it's called instruction level parallelism. There are a lot of problems, also things that you worry about. First of all, you have to have enough instruction level parallelism, because the instruction you get is the sequential stream. You say one after another. When you write your program and compile, it looks like you have to run one instruction, finish it, run another, run another. So in order to run parallelly, you have to find things you can actually do parallelly. That takes time. And of course, between hardware and software, you have to maintain that preserve order of instructions, because you want to make sure that it looks like and it feels like you ran one after another after another. You don't want things to run in a haphazard way and create arbitrary results. And so you have to, again, things like this data dependencies, control dependencies has to be satisfied when you're getting this parallelism. So, so data dependence say there's a hazard, and determine which order you can run things. So if, for example, output dependence, say, look, I can't just run them parallel. I have to make sure one after another. You have to get all those things down. And also, if you have a lot of dependency, it kind of gives you a bound how much parallelism you can get. If things are all one dependent against one after another, you can't run them parallel. You have to wait till one finishes to run another one. So by looking at data dependencies, you can figure out, okay, look, whether I get good performance, good ILP or not. So what you want to do is exploit this parallelism, but preserving the program order, and basically make sure that you always get the same result in that. So one way of getting parallelism that is in modern process is called multimedia instruction. It's called SIMD in academic circles, something like single instruction, multiple data. And it's called data level parallelism, and Intel, of course, has to give their own name. They call SSC, they used to call it MMX. So the idea there is, look, they are building these wide machines. They can easily build 128-bit wide registers. But you most probably don't need 128-bit data, because that's too big. But they can build these large things. And most of the time, you're probably happy with about 32-bit data. So what MMX says, wait a minute, you build this wide thing, but you can chop it into 4 pieces or 8 pieces or 2 pieces, what you want. And so here we chop that large thing into 4 pieces. And then what you can do is in a single instruction, you can, instead of doing one large add, with the same type of adder, you can add 4 separate things, 4 small parts. So you're issuing add, but instead of adding 228-bit data, what you're doing is adding here 4 32-bit data. the entire architecture looks very identical to adding 228-bit data. It's basically, if you remember your 004, it's like a carry chain, just have to cut the carry. You don't have to carry, you don't carry from here to here and do that. So this is, you are loading this large chunk and you are just working on these things, and voila, by doing that, having the same kind of circuitry, you get much better parallelism. And if you have like 8-bit data, whoa, you can get a lot more parallelism. So there's all these multiple instructions in there. And so what you can do is, if you have a loop like this, so you can, every iteration you can add AI to BI and put it to CI. So you can do one at a time, but assume the other 2-bit values. Instead of doing each single instruction, you can load A0 to A3 in one go, B0 to B3 in one go, just do the add of all 4 in one go, store it. So in single time, you get 4 things done. So this is really cool. And if you remember my first lecture, we showed this matrix multiply. If you get vectorized in there, you get a lot less instructions executed. We got a nice speed up. And so I'm not going down to, so the top half I'm showing the C code for that loop, and then the bottom half in there I'm showing the normal assembly that without vectorization what you will see. And once you start understanding assembly a little bit more, you can go and read this and see what's going on. And then if you vectorize, you get a humongo beast like this. This has unroll, vectorize, whatever. And this is the kind of code that get generated by after vectorization. And that runs much, much faster than the one in the left. Any questions so far? Okay. So when you have this superscalarness, when multiple execution units, so what you can do is, in a clock cycle, you can do a lot of things. So in the Nahalem processor, you have basically 6 things, 6 execution things you can happen in one clock cycle, not the same thing. So you can do a data store, you can store address, load address from there, and then you can do 3 different type of executions. You can do, there are 3 units in here. In here you can do either integer or SSC, add or move instruction. This unit can do this kind of instruction. You can have a floating point add in around here. This one is also has this bunch of different things you can do. So this hardware, complex hardware will kind of figure out, okay, if you have these instructions, figure out what of these execution units are available. If the instruction is able to execute, it will put it into one of these, get the results out. So if you are lucky, what you can see is you might get about 6 instructions going each cycle. So if you look at the measure what we call clocks per instruction, it will be 1/6 if you are lucky. If you can run the machine into the metal, that means everything is working all the time. It's very hard to find that kind of programs, but we'll see whether you guys can get something like that. That would be really cool. So what happens is, to get this thing, they do things called out of order instructions. So what that means is issuing this varying number of instructions in a clock. In here, in the Nahalem processor, you can store 128 instructions in this called instruction buffer. Actually, they have a name, better name than instruction buffer. Let me see that. Oops, it's very far up, but let me go up there. Sorry. Ooh. Okay, here. It's called a reservation station. So when you put it in, all those things are in the reservation station, ready to get, and the minute it becomes available, that means all the data is ready for it to run, you can basically issue that and run. So what you're doing is, in this hundreds of instructions, you are figuring out the patterns you can run, and the minute some part is available, the data becomes available, you can run that. And so that means the program might have instructions in certain order, it gets executed in very different orders than what the program has. So that's what you can get things like rename registers to eliminate dependencies, out of order execution. And sometimes you might run speculatively. You might not know. You might have the data, but there might be a control dependency. You might not know that it's actually supposed to happen. But you said, wait a minute, I have an execution unit available. It's not doing anything. Okay, let's run it and keep the result. And if it is actually useful, we'll use it. Otherwise, we'll throw it away. So you can do things like that. And that's for speculation. So another type of speculation, speculation mostly means you want to do something, but you don't know whether you can do it. So how do you go about doing that? The way that Intel process and modern processor do it do a lot of predictions. It's like this soothsayer, look at the crystal ball and say, aha, this is the future. And it do that really well in many things. So it do things like branch prediction, value prediction, prefetching. So it says, aha, I don't know where you're going, but I think you are going home after the class. And probably if I say something like that, that's probably right for most of the people. And actually, no, in this class, most of you can probably go to sleep after the class because of the project. So if I do that, probably I did a very good prediction. How many of you are going to go sleep after the class? My prediction is not that good. Okay, we'll see. So you can do all these kind of things and identify normal behavior of programs to deal with that. And what prefetching says is, if I look at what you have been taking from memory, there's some pattern. And I'm expecting you to continue that pattern, and I will basically get the data even though you haven't asked for it, because I'm expecting you to be doing that. It's like a very good butler who can kind of really think before you ask something, have that ready for you, basically. So by doing that, you can get much better parallelism. Because now you're not waiting for that actually to be sure that you can do it. You're just kind of doing this, assuming you might be using it, and if you do it really well, you're actually going to use it, and that will be useful. So for example, even things like value prediction. Value prediction says, so somebody figured out, when you do this complex calculation, most of the time data is 0. You multiply and adds a lot of zeros in if you're doing spreadsheets, all these big calculations. So if I don't know the value, let me assume it's 0. And that actually works most of the time. Or you look at last couple of times what has happened to that register and say, let me predict something. And people find these kind of things, there are a lot of patterns in people's program. And if it works, that's really great. So in speculation, what you do is fetch, issue, and execute as if the branch was, I already knew where it is going, by using the prediction. And if I just do dynamic scheduling, I am only doing fetch and issues. I am not going to execute until I know everything is ready. So speculation goes one step beyond. It's what we call a data flow execution model, the dynamic scheduling. That means minute the data is ready and everything is ready, you can execute, even though it might not be in the same order of the program. It might be much later instruction, but if it's ready, you can execute that. So again, the Nahalem pipeline, you can do 20 to 24 stage or 16, whatever is correct. The other thing it does is this crazy thing called micro-ops that puts everybody out through a loop. So what happened was, this is kind of historical. Intel, long time ago, came up with this x86 architecture. They came up with this instruction set. That instruction set is called a CISC instruction set. It's a complex instruction set architecture. What that means is there are these instructions there that are really, really complex. You can move an entire string from one place to another in one instruction. The problem is most instructions cannot be done in one cycle. So what modern Intel processor did was they built a JIT compiler into the hardware. So what happens inside this process is take these CISC instructions and compile them down to this thing called micro operations, that each operation is small, can be done in basically one cycle. So it's doing this mapping in there. And then inside the computer, it's basically dealing with micro ops. So up to here, there are, here's my point. So up to about here, it's dealing with these long instructions, and here it's pre-coding and decoding into micro ops. So after that, so if it says, so what that means, every cycle it can issue 6 micro ops. So there might be 6 instructions, 3 or even 1, depending on how many micro ops there's instructions. So if you look at the instruction manual in there, if you want to look at, you can see how many micro ops each instruction is going into. And if there's a lot, that means those instructions are slow. And you can have this 128 micro ops waiting to be executed, sitting in this reservation station. Basically, they are waiting there. Minute the data is available, they go, and then a slot available down, it will go down, get executed, and come back. So branch prediction, basically, the problem with branches is if you have this very nice pipeline, what happens is branch target is not known until this target detection time. Where's my mouse? Okay. Until this point, I don't know whether the branch where I am supposed to go. Okay. And so how do I go fetch an instruction, because I don't know where I'm going until this point. Inverse, I might not even know address. Some branches are saying you are going A or B, you are taken or not taken. But sometimes there might be indirect branches. I don't even know if I'm returning the return address in the stack. Until I go fetch the stack and load it and all those things, I don't know where I'm going. So I don't even, so I have to wait until this point. So if I do it, basically I have to wait till this pipeline. All these things are going to get stored. Nothing happens in here. This is 5 stage. When you have a 20 stage pipeline, you are waiting 20 stages just stalled, doing nothing. And then there's Superscalar plus 20. So that means 20 cycles without, there's 6 issues you can do. So 6 plus 20 is 120 possible instructions wasted. And it's a lot of waste. So you don't want to do that. So what you do is you build a predictor to figure out which direction the branch is going. And depending on the one predictor do, and the neat thing is these days, these predictors are really, really good. They can predict up to 99 points plus percentage where you're going. So it's like me telling you, you guys are all going to sleep afterwards, and this is going to sleep on me. What you do is, what you can do is predictor will say, aha, I tell you, you are going in that direction. This is like going to a soothsayer saying, I think you're going that direction, and then you just go there. And 99% whatever time, you're okay. And when branch is finally decided, you can say, oh, that was right, I go. If you are wrong, you squash everything and restart. And so modern predictors are these very complicated beasts. It look at things like what happened previously. It look at a thing called stack, where are the call stack, what went into the call stack, and then when you're returning, you can predict where you might be returning. Lot of different things go in there. And in fact, this is the core microarchitecture that came before Nehalem's predictor. And Nehalem predictor, they say, oh, it even has more things. And so it's even more different. So these guys are doing these complex things. What that means is sometimes it affects the programming in a way that you think, oh, this is something that I don't know what might happen. There's this condition I might not know what might happen. But modern predictors sometimes surprise you and say, I know there's a pattern, I recognize that pattern, and I go about that. And every architecture, I try different kind of patterns, and I find the architectures get better and better. So for example, at some point, if you go odd, even branches, assume I have a loop. I say if I is odd, go in one direction, otherwise not. Pentium 3 type same, okay, it just threw up its hands, because every time it's doing something different, I don't know what's going on. Brown Pentium 4, it says, there's a pattern, odd, even, it can figure out. I think Core 2 figures out things like every third, every fourth type patterns it figures out, and then things get bigger, better and better. Like these very complicated patterns you do, these guys manage to figure out. So which is kind of fun to see what it can figure out, what it can't. By writing very small program, you can get that. And I will show some of that. So the next thing that you have to worry about is the memory system. So the memory system, if you want to build a computer, what you want to do is have a lot of very fast memory very close to you. You can do that, it's going to be very expensive, and sometimes physically you can't even attain that. Because by the time you build a lot of things, it's actually already far away from you, because you're running very fast speed. So the way you deal with that is building caches. That means you keep small amount of things close to you in there, and you put things in that cache in a way that hopefully those are the things you will be using anyways. So it works very nicely. So the reason that can be done is in programming, when you run a program, there are 2 types of behaviors that it has to take advantages. One thing is called temporal locality. What that means is most programs, if you use some data, there's a good chance you are going to use the same data very soon. Okay, because normally there's a thing called a working set. I'm working with certain set of data. I'm basically touching these things again and again. So if I use that, I'm going to reuse that data again. So that means I want to keep the data that I used close by. Other one is called spatial locality. That means if I use some data, your neighboring data, I have a very good chance that I might be using a neighboring data item. Because if I'm accessing a structure or an array, okay, if I'm accessing something, I might be accessing the neighbor thing next. So that's what's called spatial locality. And taking advantage of these two, you can build this very fast memory system that feels like you have a huge amount of memory very close to you. Of course, the opposite is true. If the program doesn't behave like that, it looks like you have a lot of memory very far from you, and then program becomes very, very slow. And this is how because memories didn't speed up as fast as processors. So what that means is every generation, the memory they are further and further away, slower and slower and slower. And this is how we manage to still keep the machines running fast. So if you look at what's going on every level, I just gave you a diagram. I won't go through detail. You can look at it later. There are caches, and each level you can keep. Higher levels you can only keep very small amount, like registers. You can only keep a couple of 100 bytes in the registers, but very fast access time. Then you go to caches, on-chip stuff, you can keep a little bit more, the access time go down, and then finally when you go to main memory, you can keep a huge amount, slow access. Even at the end, like something like tape, you can keep huge amount of stuff, almost infinite amount of stuff. But it takes hours to get the tape access. It's not something in there. So there's this hierarchy. And there are certain amount of things you want, something you are using immediately, very fast, you don't want to put it in tape. But you know something that you might access in a year, that's probably a good place to put it. So there's this hierarchy in there. And when you have a cache, what happens is you want to give the illusion everything is there, but when you go to access it, the data might not be there. It's not there. There are many reasons it might not be there. So let's go through some of the reasons. So one thing is called call miss. That means this is the first time I've seen that data. So it cannot be in the cache. It's the first time I'm asking the data. It's probably sitting very back in main memory or somewhere in the disk, and now I had to go get it. One way to get around this problem is prefetching. So if I keep accessing this data, I say, aha, you are accessing this in this pattern. And there's a good probability the next pattern is here, and okay, go get it very fast because you are coming in that direction. So by doing prefetching, you might be able to get rid of call misses happening. Then there's a thing called capacity miss. What that means is you are accessing a lot of data. At some point, you have accessed enough data. Everything you access cannot be fit in the cache, and you have to throw out some of the data to put the next one in. So most caches use a policy called least recently used. That means the data that you haven't touched for a longest time get thrown out of the cache. But the problem is at some point you're going to come back to it. And if you come back to it after a long time, that thing has been out of that level of cache. This happens at every level. So what that means is you have a thing called a working set that you keep working again and you are using. If the working set is a little bit larger than the cache, when you come back to that, the data is gone. It's not in the cache. So you want to kind of create a working set that fits in the cache nicely at every level basically. You can do something like things like prefetching and get around it, but if you can avoid capacity miss, that's really nice. Then there's a thing called a conflict miss. One way of cache work, it doesn't let you store everything in every location. Sometimes there are some locations in caches which call associativity. Did you guys learn associativity in 004? Okay. Associativity. Okay, I will get again, I will talk about cache associativity now. I'm going to talk about memory system later, and we'll get there. And what that means is this is a really bad behavior because you are trying to only accessing small amount of things, but it cannot fit into it. All the data, all the aggregate can fit into the cache. The pattern makes it only fit into a small part of the cache, so you have to throw the data out. I'll get back to this later. I'm just going to put it there. And then in a multi-process system, if you're using multi-cores, there's a thing called true sharing. That means I touch data, my core, and the next time your core wants to touch the data. So I have to give the data to you. So you're getting cache miss. And then when I want to use my data, it's in with you. I have to get it back to me. So I'm kind of using data back and forth, back and forth. Okay? So that's called true sharing. And a more hideous form of that is called false sharing. That means most of the data is in a cache line. Okay? When you move data, you move a cache line. So what I am doing is I am using my data, myself, and you are using some other data, but unfortunately they are in the same cache line. So when I say, okay, I want my data, I get the entire cache line, including your data. And then you want to use your data. You say, oops, it's not with me. I have to get, and then that means the entire cache line go to you, and then at that point I don't have my data in my cache. So this data is going back and forth, even though I never touch your data. We have two separate data, but it's going back and forth. I will get these things in a lot more detail in later lectures, so this is kind of giving outline. So there are all these different ways that the data can be not in the cache. So here is what the processor you are working looks like. There are 6 cores, and there are L1 separate instruction and data caches, and then there's L2 unified cache per core, and there's the L3 cache for all the cores, and then there's main memory. So it's even this deep cache hierarchy going on there. And then right hand side, I kind of showed the difference. And the interesting thing to realize is the L1 cache delay is about 4 nanoseconds. It gets little bit 2.5 times slower when you go to L2 cache, and about 12 times slower when you go to L3 cache, and even more slower when you go to main memory. So you have, every time you go down, it gets slower and slower and slower in there. That's basically the gist of it in here. So I want a question.
Each core has 2 L1 cache for instructions and
Instruction and data.
Oh, okay.
Data cache. So instruction goes one direction, data goes in one direction. So next, I want to talk a little bit about profiling. So project 2 is going to be, the first part of the project 2 is all about profiling. Profiling is very important because you run a program. It doesn't do well. So how do you know what's going on? First of all, do you know even it's not doing well? And if it is not doing well, what's the reason? So just having one number at the end saying it ran in 10 minutes versus 5 minutes doesn't tell you too much. You don't know what to look if you have a large program. The profiling means looking at what the program is doing to get understanding in there. So what you want to do is collect this performance data while running the application. And then if you have a large application, you want to organize and display data in variety of ways, and a lot of times relate that data to source code and to see what that means in the road code. And hopefully by looking at this one, you can identify, aha, there's a problem here. So there are a bunch of tools, Intel vTune, gprof, oprofile, perf. So you guys are going to use mainly perf, and we will probably talk a little bit about gprof. And next time when you come, next lecture, we'll talk about this a lot more. So profiling is mainly to find where in an application or a system there's a significant amount of activity. And when there's a significant amount of activity, you want to know whether those activity can be avoided or there's a problem in here. So there are some 3 issues in it. Where significant activity, what's where? It could be anywhere. It might be addressed in the memory, something might be happening. It might be, if you're looking at the entire system, some kind of process in there. In the operating system, it might be happening in one thread. It might be happening in an executable file or a module. If you know the symbols of you can say, oh, that module, that actually is this function. And if you know even more information about the program, you can say, aha, that function, in fact, is this line of the program. So you get this information from the application when you compile that you can say, debug information, say, aha, this happens in this line of the program that's having this problem. So you can break it down and get that info like that. Somebody's trying to call me. Okay. Second is, we care about significant activity. If the activity just happen only few times, happen only nanoseconds of execution time, who cares? You don't want to do that. You want to focus on things that matter. And the key thing about this card is that triage. If you spend most of your time for insignificant things, you will get insignificant performance improvement. If you found the significant part and work on that, you can get significant gains. So key thing is to find the significant part. Excuse me. Okay. And the final is activity. So activity means time is spent in doing something, and some activities are bad ones. Like if you actually do running instructions, that's good. If you're running some useful instruction a long time, you're okay. But you might doing activity like cache misses, branch misprediction, stuff like that. That's bad activity. So you want to say, aha, I'm spending a lot of time doing something that I can avoid, and how do I avoid that? So that's what you want to look at. And you have two ways of doing that, and I want to give you an analogy to kind of figure out what it is. So assume you are going visiting bunch of different places. Okay, you are on a city tour. You are visiting different parts of the city. And I want to figure out where do you spend most of your time. Okay? And that's a hard problem because I am sitting in my office and say, okay, you're going visiting the city. I want to figure out where you spend most of the time. I have two ways of doing that. I'm a busy person. What I can do is every 30 minutes, I can call you and say, where are you? And you will say, okay, I'm in this library, I'm in this, and then at that point I can add a histogram and say he's still in the library. And I come and call again, where are you? And I can mark that. And at some point at the end of the day, I'll have a histogram saying every time I call, you found something. If you spend a lot of time in the science museum, I will have a bunch of excess in the science museum, and then that will become, and if you are not into art, if you have only one tick on the Museum of Fine Arts, okay, you are not spending time there. That's one way to do that. That's called statistical. So other way is saying for every landmark, I create a telephone booth. And every time you enter a landmark, you first have to go to the telephone booth. You have to call the operator and say what time it is, so you look at the watch, and then you call me and say, aha, I'm entering this landmark, the time now is 5:50, and I write it down. And every time you exit the landmark, you call me and say, I'm exiting this landmark, time now is, I write it down. Okay? So these are the kind of two ways of doing that. That's like an instrumentation solution. So the sampling collector basically periodically interrupt the processor and look at where you are. And depending on where you are, you can mark that up. And it's called time-based sampling, means every time, every 100 milliseconds or something in certain process settings, you stop and say where you are. Event-based sampling means you are counting number of events like cache misses. Every 100 cache misses, you stop and say, okay, where that happened. Of course, if the cache miss happen in a regular pattern, you might be in trouble because every 100 you might be in the same place. Then you will get a skewed number, but most probably there's a statistical variation in there. You can get a count in that and figure out where these things are happening. So if you are looking at where all the cache miss is happening, you don't look at every miss because there are millions of miss. Every 10,000 miss, you figure out where you are, and statistically, if one is missing many times, that will add up in that column. And nice thing about that is there's nothing you need to do, no installation, no changes to application you need to do. In here, they do not have to go change these phone booths everywhere. Wide coverage, you can cover everything. So that means assume I install phone booths in all the fixed landmarks, but there's a circus that came to town. I didn't see. I don't have phone booth there. But here, if I'm calling you, I know I'm only touching you. Any place you are, I will cover, even though I haven't anticipated that one. Very low overhead, because I can decide to call you every 30 minutes or call you every 1 minute if I really worry about you, and I can control the overhead I'm looking at this thing. The problem is it's approximate precision, because if you only spend if you spend 5 hours at MIT and 30 seconds at Harvard, I will never know that you went to Harvard because I might have not called you while you are there at Harvard. You might think it's boring and come back and hey, I never knew that you did that. And also other thing is I don't know exactly how many times you went to a place, because I might have called you 10 times and I found you in a Museum of Science 10 times, but you might have gone there 20 times. And I might have missed you on the other times I didn't call, or you might have gone there only 5 times, you stayed for a long time, and I might have called multiple. I don't know that. And I don't know the count of times you have gone, which is hard to know. So main thing is there might be things that are not that statistically significant that you might miss. And if you care about that, this is not a good method. But most of the time we care about that really statistically significant thing, so this is a really good method. The other part is perfect accuracy, because every time you go somewhere you have to call me, and I know that you went, how many times you went to Museum of Science, I know exactly how many times you enter and exited the procedure, I know all those information. The problem with that is it's kind of low granularity. I can't put phone booths at every corner, and if you have to call me at every corner, it's going to be way too expensive. So I have low granularity, very good information, and also high overhead. Because if you are going in and out a lot to a building, you have to call, you have to stop and call, it's very high overhead. And there's not much of a way for me to control that. And it's also high touch. That means I had to build all that infrastructure. I had to go and modify your applications basically in something like gprof at compile time application get modified to basically have all these counters installed into the application. So you can look at a lot of different types of events. So in Intel, if you look at it's called performance counters, there are hundreds of performance counters. And some of these performance counters has no sense whatsoever. So for example, Intel has this counter called number of bogus branches. What's a bogus branch? I mean, why should Intel be doing anything bogus? It's some architectural name they came out. But there are some counters that are useful. So instead of getting overwhelmed by thousands of things available, just focus on things that we care about, things like branch events, load store events, cache misses, prefetches. Those are the important things, and some multi-core events that we can look at and get some interesting information. And a lot of times, just by looking at numbers doesn't make too much sense. You know you had 5,300,000,000 branches missed. Is it a good high or low? We have no idea. The right thing is, okay, with relative to number of instructions executed, how much it would be. So most important numbers are ratios. So from the branches executed, how many were missed? That's a lot more important than you have 5 billion branch misses. Okay, that doesn't say anything to me. So most of the time you have to figure out the right ratios and what makes sense to look at those ratios. So now what I want to do is go through a couple of examples and show what I can see in these different program behaviors. Any questions so far? Next lecture we are going to go through hands-on examples on going through some of these profiling tools. So this is kind of fun thing. This is kind of what I did was trying to discover what architecture is doing and what is the modern multi-core is capable of doing. In fact, some of these examples, this set of examples were done on a Core 2. So some of the numbers might be very different in Nehalem because the architecture might do better in especially some prediction stuff. I don't know. It might be fun to do it again. So what I have is a program that I first created 2 interesting arrays to access this array A. One array has numbers 1 to n, max A stored in this array. This has 1 to max A in a random order stored in this array. Okay? So when I use this as a way to access the main array, if I use this inc A 0 to n, I will actually access A also 0 to n. It's almost like saying AI, but I use this here. But if I use this one, I am doing random access. So the first program I am doing is just nothing but just going through this once. Basically, I will have outer loop that will go through many times, so I can actually measure some time. So I just go to just nothing but I'm just going through that. Second thing I did is I just put a condition. Say j is less than max A half. That means halfway through the program, I will go and update this one, and other half I am not doing anything. Then I said, okay, look, I want to divide by every 4th element. So what I do is j and with 0, 3 in there. That means 3 means 2 bits. So in the 1, 1. So if that is 0, that means last 2 bits has to be 0 to formate that. So every 4th element I will update. Otherwise I don't. And the next thing I did was I updated. Okay, let me ask you a question. So this program, the output, that means what happens to A, the output of A is equivalent to some other program, one of these 3 programs. Which one is this output equivalent to? See whether you can wake up. So every other program will do first 3 programs, or each will have different outputs. A array would be different at the end of if you run it. Except the 4th program will produce the exact same results as some other program, the first 3 programs. Which one? Wake up, wake up, wake up. I hear something, I hear some second one. Somebody says second one. Okay. How many people agree with that? How many people disagree? Okay. This is not a statistical sample, it can be exact. Why is it the second one? Second one is right. So what that means is, in fact, instead of a j, I am using int j. Int j is exactly j because it goes int 0 is 0, int 1 is 1, int 2 is 2. I just created the same darn array in here. Just did something to get that. Okay. And then finally, I am doing the rand a, basically is on max a. So what that means, I am using the same amount of data will get updated, but it's very different order in there. So now, let me, before I go to the next slide, question.
Maybe I just missed when you said this, but what is the A array? Because it doesn't look like
A array some numbers, some random set of numbers. I don't care about that. I just updated those numbers. So in here, which program do you think run the fastest? So let me ask you, okay, which program updated the least amount of and updates for A? Third one, yeah, because it's only doing every fourth element. Which do the most? First one is doing every element, and everybody else will do probably half of the update. So that knowing that, which program will run fastest? First one, it's updating everything. First one fastest, okay. Somebody says first one, okay. Which program will run slowest? Last one. Ah, you guys are onto something. Either you have seen my slides or you actually know what the hell is going on. So what I show here is, I will, you can't read this one, but I got a runtime and then I created a ratio. So if you look at the ratios, so the first program I always normalize to that, runs 1, and that ran the fastest, which is right, and the last program ran the slowest. And the interesting thing is, the test J, the two, the second and fourth one, that wrote about half the arrays basically ran all the same, but the one that wrote every fourth element was actually slower than the other two. So why is going on? So what you can do is first look at how many instructions were retired. That means how many instructions got executed. So if you look at that, what we see is the first one execute the least amount of instructions because it doesn't have to do all these conditions even though it's updating. The interesting thing is the second, the one that wrote half has the most amount of instructions. One that wrote only 1/4 has middle amount of instructions. That kind of makes sense in here. But this still doesn't explain the slowdown. That means if this is the only case, the divide by 4 should run faster than on the other three. That doesn't make sense. And then what you look at instruction branches in there. And if you look at the branches, what you see is, let me skip this one. Actually, I want to get to this one, which is called clocks per instruction. What this says is, if the instructions ran slow, each instructions will take a lot more clock cycles. That means the instructions are not doing well. That means they are stalling, they are taking a lot more time. Normally, you should be able to run in this architecture about 4 instructions each cycle. You should get a CPI of 0.25. But that's very rare. And if you look at that, if I normalized, I get 1 in here normalized. And then what you see is the second and fourth has almost the same CPI. And the third has worse, and the last one is even worse. So why is that? Why are those instructions doing bad? And then you can go look at misprediction instruction. And this is exactly what happens. Divide by 4, there's a condition. The branch predictor couldn't predict that well. Because it probably predicted the first 3, and then it predicted, okay, after 3, next one is also going one direction, oops, it's in the other direction. Okay, going first 3 prediction, going one direction, no in the other direction. So divide by 4 was really bad at predicting. And then the random one was just completely off. Random one, basically, prediction was really, really off. That's why this is. So in fact, if you just want to calculate the runtime, if you think every misprediction cost you 21 instructions, you kind of get the exact total cost you can calculate. So you assume each instruction take 1 cycle, and every misprediction instruction take 21 cycles, and you just calculate that. And this is kind of, I just took it out of the hat, and then voila, I get a number that's very close to the runtime. For that, what that means is, is I can kind of understand what the behavior, this explains what's going on. So I can have a model in my head for what's going on. It's all about misprediction in here. I did 2 other experiments in here. I have the slides in here, but I don't think I have too much time to go. I want to go to the numbers in there. Are you ready, John? Okay, why don't you go put your laptop in? Do you have the dongle? Okay. So voila, okay. So something you guys waited all this time and were up all these days developing. So let's see how everybody did. Okay, without further ado, I haven't even seen these numbers. Okay, what happens? Okay, it's trying to, okay, good. It's got the screen, okay. Should have it, okay.
Something to keep in mind is we haven't actually investigated what's causing people to have build failures or crashes yet, so it could be your fault, it could be ours, we'll figure that out.
So is smaller better or higher better? What's
better? This is runtime.
This is really good. This is actually.
The baseline is the plateau that you see in the middle.
So this is really good. That means there were like kind of 2 groups. One, most of the people got everything right in there and at the bottom, and there's another group that missed something and is in the second camp.
I think there's also some of these projects are from people who dropped the class or at some point. So there's probably some of the ones that we did might not be actually representative of what's going on in the class.
So this is, because last year we got like almost exponential curve. Actually, last year what had was there were a couple of people at the bottom and everybody was at the top basically. So which is actually good. So you guys actually figured out what's going on.
So next one is even more interesting. So this was the test case that we gave you guys. Most of you optimized it down to 0 seconds. So I coded in a harder test case, and here's the results on that. Still pretty good.
So.
There's some very specific optimizations that
Yeah.
So that, yeah, exactly. I mean, the people who are climbing up, I don't know exactly what, but that's very clear that some person, probably some data representation hack that people missed in here. Yes, which is really interesting. Yes.
And then for Pentominoes, this is very incomplete because the set of tests that we wanted to run are still currently running. So I just picked a random test case just to give everybody an idea of how everybody did, and set the timeout very low so that I could actually finish it during this lecture.
And what is it, 0 seconds?
Yeah, somebody solved it instantaneously. It searches for the first 5,000 solutions to some random puzzle that I pulled out.
So, are they getting correct answers?
That I haven't verified
So,
yet.
so it might be, there might be just crashing, so we don't know that, whether they're getting correct answers, but.
Which one is the baseline?
The baseline is actually the 9-second mark.
So somebody was slower than the baseline?
No, 10 seconds and above are either timeouts
Oh,
or
timeouts.
fails.
They're probably mostly timeouts.
Yes.
So there you are. This one, people will have some work to do, I guess, to get the performance down there. But this is pretty good. This is not like there's no 1000x off. I mean, last couple of years we had people. There was somebody who was 1000x different. You had to plot it in a log thing. So in fact, if I do a square root, which in the grade, this is pretty nice. So even 8x off is not that bad. So this is great. So this is where you guys stand in performance-wise. And so if you are in the bottom, you can go have a beer. Otherwise, you might have to go back and figure out what you missed. Or if you're overage, yes, exactly, yes. I shouldn't say, I should say that.